Welcome to part 3 of the lecture on global register allocation. Last time we discussed issues in global register allocation, the problem itself, the usage count based register allocation, then linear scan based register allocation, and part of Chaitin's graph coloring based allocation. To do a quick recap, here is the framework of Chaitin's register allocation algorithm. So, to begin with, there is a renumbering phase in which the live ranges or webs are identified. Then there is a build phase where the interference graph is built. Then there is a copy subsumption or coalescing, which removes some of the copies and reduces the size of the interference graph. Then we have spill cost computation. So, the spill cost is computed based on many heuristics. Then there is a simplification which removes the nodes and edges and reduces the graph. Finally, this entire thing the spill nodes have to be actually whatever for the spill nodes we have to introduce spill code, and the whole process is repeated, and finally the selection of registers is made. So, quickly simplification is take a node whose degree is less than r and then remove the node and its edges from the graph. So, keep going doing this until it is not possible to do anything more. So, at some point there will be nodes all of which are of degree greater than or equal to r, the number of registers available. So, in such a case we need to spill a node. Spilling a node implies loading x into a register at every use and then storing x from register into memory at every definition. Spilling cost is very simply computed as cost v equal to sigma c star 10 to the power d, where c the sigma is over all the loads and stores in the live range, c is the cost of a load or store, and d is the depth of nesting. This is basically this is used to approximate the number of iterations in any loop. There are many spilling heuristics, some of them use this area, which actually represents the global contribution by the live range to the register pressure, and it is possible to use many heuristics at different points of time. So, here is a very simple example which shows how a graph which is 3 colorable can be colored without spilling. Now, here is a graph which is 3 colorable, but it cannot be colored by the coloring heuristic. It says we will need a spill, but obviously as we have shown here it does not need any spill. So, there are some heuristic improvements possible to the heuristic itself, which will help us in coloring such graphs. We will see that a little later. How to spill a node? To spill a node, we remove it from the graph and represent the effect of spilling by reloading the spilled object at each use and storing it in memory location at each definition point. So, now the problem is this creates new webs with small live ranges, but which still need registers. So, after all the spill decisions are made, insert spill code, rebuild the interference graph and then repeat the attempt to color. When simplification yields an empty graph, we stop. So, let us see the effect of the spilling on webs. Here is the web example that we had seen before. There are many webs here W1, W2, W3, W4 in different colors. So, most importantly W1 consists of this def, this use and this def, and similarly the others. So, suppose x is spilled in the web W1, what happens? So, here is the effect of that, but before that this was the interference graph created for this particular web without any spilling. So, if x is spilled and now there is a def x, so obviously we need to store that x into a location, let us call it as temp. Okay. So, now this is a definition point of x and we have stored it into memory. Here is a use point of x and we are actually reading it from memory, x equal to temp and then use x. So, here is again another one, x equal to temp and use x. So, this def x is again a definition point. So, we are storing it into memory by saying temp equal to x. The others are not spilled. So, only this particular web is spilled. So, all the loads and stores are appropriately taken care of. So, now there are many webs here. So, the webs actually get split into many. So, whatever is shown in red, def x and temp equal to x is a small web on its own, you know. So, this is x equal to and this is temp equal to x. So, there is a computation and then a use. So, this becomes a small web on its own, and here is another small web, a third small web, fourth small web, and the rest of the other webs remain as they are. So, there are now 8 webs, and then of course, the temp equal to x, x equal to temp, temp equal to x, x equal to temp, these 4 now become a separate web, consisting of these B2, B3, B4 and B5. So, with these 8 webs, now the interference graph slightly changes. In this case, there are many nodes, there are if you are the same number of edges really speaking, but in a very large set of webs, in general the interferences will reduce and the interference graph becomes a little more sparse, possibly easier to color. The coloring heuristic is simple. There is a repeat until loop. So, all the vertices are now on the stack. So, take a vertex from the stack. So, the colors used V is the colors used by the neighbors of V. So, in the graph, colors free V is all the colors minus colors used, and color V is any color in colors free. So, we keep doing this until the stack is empty. So, that would give us a coloring, which is a fairly straightforward process. Convert the color assigned to a symbolic register to the corresponding real register's name in the code. So, we rewrite the code and that completes the coloring heuristic. Now, let us take a complete example of a program, start from identification of the live ranges, building the interference graph, then coloring the graph and so on. So, here is a very simple example. The program is in intermediate code. So, here is T1 equal to 202, I equal to 1, T2 equal to I greater than 0. So, then there is a test if T2 go to L2. So, if we cross 100, then we go to L2, otherwise we keep looping in this particular loop. So, T1 equal to T1 minus 2, T3 equal to address A, T4 equal to T3 minus 4, T5 equal to 4 star I, T6 equal to T4 plus T5, star T6 equal to T1, I equal to I plus 1 and go to L1. So, this is the loop. There are 1, 2, 3, 4, 5, 6, 7 variables here, and here are the live ranges of the variables. For T1, the range is from 1 to 10. So, here is a definition, the first definition, and the last use is in this number 10. For I, it is from 2 to 11. So, here is the first definition and the last use. So, that is 11. And then we have similarly T2, which is a very short live range. T2 is defined here and T2 is used here. So, 3, 4, that is it. T3 is 6, 7, similarly defined here and used here. T4 is 7, 9. So, T4 is defined here and used in 9. T5 is 8, 9. So, T5 is defined here and used here, and that is all, and T6 is 9, 10. So, T6 is defined here, and star T6 means you read T6 and then do indirection. So, this is really usage of T6. So, this is the live range of this particular variable T6. So, for these live ranges, it is easy to see the interference. So, for example, almost every variable overlaps with the live range of T1 and I, because they run almost throughout the program 1 to 10 and 2 to 11, all others are in between, we can easily see that. So, for the two nodes T1 and I, there are edges coming from every other node. So, say for example, from T2 there are 2 edges to T1 and I, from T5 there are 2 edges to T1 and I, and so on and so forth. And similarly, for T4 and T5 intersect, because this is 7 to 9, this is 8 to 9. So, there is an overlap. And then the others, for example, T6 does not interfere with any other node except T1 and I and so on. So, these live ranges are all small, and but still coloring this with 3 registers is not a trivial job. So, let us assume that there are 3 registers and nodes T6. So, what we do is pick nodes with less than 3 degree, that is 2 degree. T6, T2 and T3 have degree 2. So, these 3 are actually deleted from this particular graph and pushed on to the stack. So, that is the first thing. So, they have been shown in blue. So, after this is over and the edges corresponding to these are all removed, the graph reduces to this. So, this is a complete graph, and this cannot be reduced further. Spilling is necessary because every node here has degree 3. So, now we need to compute the using the cost of spilling using the spilling heuristic. So, let us use the simple Chaitin's heuristic of sigma c star 10 to the power d. So, node T1. So, let us look at the number of occurrences of T1. So, these are the only 4 nodes for which we need to compute cost. We need not compute cost for those nodes which have already been deleted. So, T1 occurs, let us assume that the load cost and the store cost are the same. So, T1 occurs once in this instruction number 1, then it occurs in instruction number 5, and this is twice really, and then in instruction number so we can actually in this 10 as well. So, 1 is here, and then inside the loop, so we have 1, 2 and 3. So, 3 occurrences of T1. So, that is 31. So, 1 plus 1 plus 1 plus 1 star 10, that is 10 to the power 1, right. So, this becomes 31. So, similarly for I, here is 1, and within the loop there is one occurrence here, another occurrence here, third occurrence here and a fourth occurrence here. So, there are 4 occurrences. So, there are 4 ones here. So, 1 plus 40 is 41. So, T4 has a definition here and a use here. So, there are only 2 usages, 2 of these. So, 1 plus 1 star 10, that is 20, and then similarly T5 is also T5 is defined here and used here. So, 1 plus 1 star 10, that is 20. So, the costs are 31, 41, 20 and 20, and out of these 2 we could have chosen, and degree is 3 for all of them. Now, H naught V, which is cost per degree, is 10, 14, 7 and 7. So, we could have chosen any one of these for spilling. So, let us assume that we have chosen T5 for spilling. Now, the once it is spilled, it is always permanently in memory. So, this is the reduced graph. This can be easily colored with the 3 colors, there is no problem at all. So, this is the stack of T6, T2, T3, then we delete T4 and then T1 and then I. So, we can easily color this graph by assigning I a color, and then we take T1, it is assigned a different color. So, that is here, and then we take T4, we assign a color which is different from each of these and so on and so forth. So, observe that T6, T2, T4 and T3 are all given the same color, that is R3, right. So, if we rewrite the code using these registers, I have not written assembly code here, but I have just rewritten the intermediate code using these registers, so that it is easy to understand. So, observe wherever we have T1 we would have put R1, and wherever we have I we have put R2. So, see that this code is correct. See, even though this 6 and 7 there is R3 equal to address A and then R3 equal to R3 minus 4. So, this is a read of R3 and then write into the same one. So, this is reused here. So, we actually, because the live range of this R3 and live range of this R3 are not the same. So, this R3 for example, live range is 6 7, live range of this is 7 9. So, there is no overlap as such, and this is a use and this is a definition. After this usage we can actually write into the same register. So, therefore, this is possible. Okay. So, this is the rewritten code which shows that registers have replaced the temporaries, but please observe that T5 is still T5. that is because it is actually in memory. When we actually generate machine code, this build node will be provided with a temporary register. So, this will become a computation into a temporary register. Afterwards T5 will be used here, and then it is discarded because it is not needed anymore. So, if memory can be used as an operand in the instruction, this does not become necessary. So, that is the example. Now, what are the drawbacks of Chaitin's algorithm? So, constructing and modifying interference graphs is a very expensive process, as interference graphs are typically very huge. So, if you take for example, the GCC compiler itself, and then for example, all the functions, procedures, etc., are combined, and you try to draw a combined interference graph, then the graph has approximately 4.6 million edges, extremely huge graph. So, this is one of the major drawbacks. Then what are the modifications necessary in order to improve this particular algorithm? So, you could be more careful during coalescing. For example, do not coalesce if the coalescing increases the degree of a node to more than the number of registers. So, if you do this, then it may lead to a spill, that is why there is no need to coalesce. Then this is copy subsumption problem. Optimistic coloring: when a node needs to be spilled, put it into the coloring stack instead of spilling it right away. Assume that it can be colored, put it into the stack, hope for the best. Spill it only when it is popped and if there is no color available for it. So, we will demonstrate this very soon. This could result in coloring graphs that need spills using Chaitin's technique. For example, here this is a 3 colorable graph which we saw before. It cannot be colored using Chaitin's heuristic, but using optimistic coloring it can be. Say one is chosen for spilling. Now, one of them has to be spilled, there is no way you can color it with the 3 colors otherwise. So, do not actually replace this and say yes it is spilled, and replace the loads and stores by appropriate instructions from memory. Push it into stack. Okay. Assume that it is colored, push it into stack. Now, we have the rest of the graph here 2, 3, 4, 5, these edges go away. This can be colored with 3 colors. So, we can say to these are the, let us say, the colors assigned to the particular graph 2, 3, 4, 5. Now, 1 is left on the stack, right. So, observe that 2 and 4 have the same color, 3 has a different color, there is a color free which can be assigned to 1. So, because we did not spill 1, but pushed it on stack, coloring of this has been possible. This is the optimistic coloring that we indicated a few minutes ago. So, but there is no guarantee that this type of a graph, for example, can color every other graph which is not 3 colorable. For example, if you look at this graph, okay, this is not 3 colorable, but if you even if you try the coloring heuristic on this, it does not work, because it is a fully connected graph. So, every time you introduce something on the stack, you are of course left with just these 3 nodes. These can be colored with 3 colors, but when you try introducing this, it will be connected to all others, and therefore, you need a 4th color for this. So, this is how we do optimistic coloring, and this is the end of the lecture on register location. So, now we will begin the new lecture on implementing object oriented languages. Welcome to the lecture on implementing object oriented languages. In this topic, we are going to basically consider classes and objects, and then see what are the requirements of the language, how to map the names of the variables and to the methods, then how to map names to methods. There are so many names in the program. It is possible that some of them are in the subclasses, some of them are in the superclasses, So, some of them may be redefined and so on and so forth. So, how to map these names to the appropriate methods is something we are going to study. Then variable name visibility, so and then code generation for methods, then finally some of the simple optimizations. Some parts of this lecture have been adopted from this book by Cooper and Torkson. So, what are the language requirements? So, in an object oriented language, we have objects and we have classes. Then, so for every class you can instantiate it and create an object. So, these are all well known. Then we have inheritance, subclasses and superclasses. So, you can actually you first declare a class, then inherit from it and create a subclass. So, the class from which I have inherited is called as a superclass. Inheritance requires that a subclass have all the instance variables specified by its superclass. So, in other words, if the superclass has 3 variables which are actually declared, then every subclass of this superclass will have all these 3 variables in it. So, this is necessary for the superclass methods to work with subclass objects. As you know, you can actually have a base class pointer point to any object of the type which is derived from this base class. If that is to be done, then the superclass methods must work with subclass objects, and this requirement of having all the variables of the superclass inside the subclass becomes necessary. This will become clearer as we go along. If A is B's superclass, then some or all of A's methods and instance variables may be redefined in B. So, that is not a problem. So, we should be able to provide for this as well. Here is a very simple class diagram. So, the legend is these 3 in blue, turquoise blue are classes, then the light brown are all objects, and then these orange colored ones are all methods. So, there are 3 classes 1, 2 and 3. Class 1 has is inheriting from 2 and class 2 is inheriting from 3, that is the end. Then class 3, which is the grandfather class, this is the father class and let us say this is the son class. So, this is the hierarchy that we are talking about. It has a static variable n which shows how many instances of this have been created, and then it defines a procedure called phi. It also defines another procedure called form. Class 2 derives from 3. It has one object of its which has been created, that is C. So, even though it inherits phi from the superclass 3, it redefines it. So, now you can see that it is this phi, this method pointer is pointing to phi, whereas form which is inherited from 3 is still being reused by class 2 also. Let us look at class 1. This actually inherits from 2. So, 2 in turn inherits from 3. So, 1 will have the variables of 2 and 3 both, and methods also. So, for example, phi is inherited, but it redefines phi. Then form is being reused, the same form which is defined by 3 is used here. Fo is defined by class 2 and it is being reused here. Phi is a new method which is defined by class 1 itself. So, and then there are 3 objects A, B and C. A and B belong to class 1, C belongs to class 2 and there are no objects of type class 3. So, let us see with this scenario how things work. It should be made clear that method invocations are not static calls. In other words, when we actually write A dot phi, we do not know which method is being called. In this particular case, this is the general statement. In this particular case, when we say A dot phi, it invokes 1 dot phi. So, the reason is A is an object of type 1 and this FEE invokes 1 dot phi, which is being redefined. Even though phi is inherited from 2, it is being redefined in 1. So, the local phi will be called when we say A dot phi, that is no problem. B dot phi invokes 2 dot 4, sorry, B dot 4 invokes 2 dot 4. So, let us see what happens to B dot 4. B is here, 4 is inherited from 2, there is no local redefinition of 4 for 1. So, when we say B dot 4, it is really 2 dot 4 which is being called. Okay. So, there is no 4 here. Then C dot fum invokes 3 dot fum. So, when we say C dot fum, C is an object of type class 2, but it does not have its own fum, it is actually from class 3. So, C dot fum really invokes 3 dot fum. So, this is what we mean, this is a virtual call. We have no idea of which particular call is invoked until the call is resolved. Conceptually, method lookup behaves as if it performs a search for each procedure call. So, these are called virtual calls. How does it happen? Search for the method in the receiver's class. So, that is the particular object. For example, if it is B dot 4, search in the class corresponding to B. So, that is 1 itself. If it fails, so for example, there is no B dot 4 in the class corresponding to B. If it fails, move up the receiver superclass and further. So, then the superclass of 1 is 2. So, 2 defines 4. So, B dot 4 resolves to 2 dot 4. To make this search efficient, an implementation places a complete method table in each class. So, this is what has happened here. Each one of the classes has a method table. So, for example, if you consider 1, there are 4 methods corresponding to class 1. First one, phi, is a local redefined method. So, there is a pointer to this. This is the method table we are talking about. Fum points to the old one itself, the inherited one. 4 points to the old one, the inherited one. Phi is a new method which is defined within 1. So, something similar in 2 also. Phi is locally redefined, fum is inherited and 4 is a new one. And within 3, phi and fum are both locally defined new methods. Or a pointer to the method table is included. So, this is called as a virtual table pointer. So, instead of keeping this entire table inside the class, it is possible to have a table outside and a pointer replacing this entire table. So, then I go to that table which is actually this, which is outside, and then call this particular method. So, that is called as a virtual table pointer. How do we map names to methods? If the class structure can be determined wholly at compile time, then the method tables can be statically built for each class. So, here in the previous example, that is how it was. See, okay, sorry. So, here we knew which particular class is where, which object belongs to which particular class, which methods have been defined in which class, etc., was all known. So, we could build all the method tables statically and put them inside the class record. If classes can be created at runtime or loaded dynamically, class definition can change as well. Then like in Java, I wrote it at runtime, I can also create it dynamically. Then full lookup in the, so if we do this, then there is no need to look up, everything actually, the method table pointers are all there. So, method pointers are all there in the method tables. So, we just go to that particular method and use it, there is no need to search. So, for example, there is no need to search anything here. I have a special pointer for firm right here, which can be used to call this firm. Otherwise, if it is dynamic, then full lookup in the class hierarchy can be performed at runtime, no problem, because if I add a class at runtime, then I may not be able to build the entire table at compile time itself. Otherwise, use complete method tables as before and include a mechanism to update them when needed. So, if we add a new class, then for all the classes actually which are derived from this class later on, we create the method table at runtime. So, that is what this really is. Now, what are the rules for variable name visibility? So far we saw the rules for searching method names. Now, let us see what happens to data. So, let us look at a picture, the same picture here. So, we have A and B of type class 1. So, A has x, y, z, B also has x, y, z of and these are objects of class 1, and then C has only x, y and it is of class type class 2. So, invoking B dot phi allows phi access to all the B's instance variables, all the 3 of them x, y, z. Why? Since phi and B are both declared by class 1. So, see here. So, we call B dot phi. So, this phi will have access to all the variables, that is x, y, z of this particular object. So, both B is of type class 1 and phi is redefined right here. So, there is no problem, everything which is declared will be accessible to the method phi. And also all the class variables of 1, 2 and 3. So, this is the lowest in the class hierarchy. So, 1 inherits from 2, 2 inherits from 3. So, all the variables of 2 and 3 will also be accessible to this method phi, which can actually access the variables of the super classes. Now, however, when we are invoking B dot fo, there is a small problem. So, let us see what happens. So, here is B and here is fo. Fo is not defined here, fo is defined actually in class 2. So, it is that fo that we are calling, and when we compile this entire thing, fo did, when we compiled 2, fo was not expected to work with 1, it was expected to work with 2 and 3 only. So, this creates some special problems. Invoking B dot fo allows fo access only to instance variables x and y of B. It does not allow access to z, because it never knew that there is something called z. Z actually belongs to 1, which actually the objects we create for of instance of class 1, whereas this fo belongs to class 2. So, class 2 has no information about class 1 as such. So, z of B is not accessible to this fo. So, since fo is declared by class 2 and B is declared by class 1, fo can also access class variables of classes 2 and 3, but not class variables of class 1. So, this is what we explained just now. How do we generate code for methods? Methods can access any data member of any object that becomes its receiver. So, what is a receiver? Every object that can find the method is a receiver. So, that we say B dot something and so on. So, that B is the receiver. Okay. Subject to of course, class hierarchy restrictions. So, whenever in the hierarchy of classes an object can find a method and that method can be executed, and methods can access any data member of any object that becomes the receiver. So, this is so if it is B dot something, then B's B dot phi can access members of B, and the compiler must establish an offset for each data member that applies uniformly to every receiver. So, the problem is if receivers are from different classes, then this creates a problem. So, you cannot access the data variables so easily. So, we will see this difficulty. The compiler constructs these offsets as we process the declarations for a class. So, objects contain no code, they contain only data, this is very clear. Code is actually in some other place. So, let us show this for a single class with no inheritance. So, here is a very simple class giant. So, int phi, int phi, int fo, int fum, 4 methods, there is a static n and int x y. So, objects contain variables x y, n is within the class record and the method pointers are all here. So, these objects point to the class record and here are the method pointer offset 0, 4, 8, 12. So, when we want to call something we know where exactly this can be done at compile time. So, if there is a joe dot something, it is very easy to joe dot phi, we know the offset of phi. So, calling taking the contents of this is very easy and then there is a jump subroutine instruction to execute this particular method. So, here is the detailed class record class diagram with single inheritance. So, the previous one did not even have inheritance, here there is single inheritance, multiple inheritance would be the last one. So, we have class giant which is of class MC, type class MC and MC itself is of type class SC. So, there is a class hierarchy of giant, MC and SC. So, this is the super class called class in Java, which is the mother of all classes. So, its own class pointer actually points to itself. So, then we have super class pointer field, then method pointer fields and then variables. So, that is how all these records are laid out. So, these are the variables x, y and z and here are the super class pointers. So, so these are the class pointers. So, they all of them point to this particular class itself. So, and for objects the class pointer points to their own class type. So, all these for example point to their own class type. How about the object layout under single inheritance? So, remember this diagram. So, we have this giant which has a new phi and phi and then the static which is not necessary for objects. So, objects have x, y, z. So, for object layout for Joe and Fred which are members of the class giant. So, there is a class pointer, then the data members of SC which is just one variable x. So, for example, here right. So, this SC has only one variable x, this MC has x inherited from here and y its own, and giant inherits x and y from the super classes and z is its own. So, we have SC data members, MC data members and giant data members. So, this is the layout for objects of type giant. Similarly, objects the class record is something we already saw, class pointer, super class pointer, new method pointer table. This is the method pointer table. Object layout for goose which is a member of MC which is one level above. So, this is MC, this is the object we are talking about. It does not have the members of giant obviously, it has super class members SC, then data members corresponding to that and then its MC its own. Then this will be of course similar. Object layout for SC, that is this particular class which has only x, it has only SC data members which is just x. So, please see that giant the order in which this data is laid out. So, when there is no inheritance, right, we have just our own class instance variables, and when there is one level of inheritance, then we have the super class data members followed by our own data members. then there is two levels of inheritance. We have the grandfather superclass data members, then the father class father superclass members, and finally our own class data members. So, this is the order in which the objects are all laid out. Now, the problem is, the instance variable has the same offset in every class where it exists in its superclass. So, SC will always be present in this area, MC will always be present after SC, and giant will always be present after SC and MC. So, this is the order in which the data will be laid out, okay, irrespective of any other inheritance as well. If it was not giant, it was some other class, say A, then we would have SC, then MC, and then A. Okay. And if there were to be some other class which inherits from giant, say B, the data area of B would have been attached here. Okay. So, method tables are similar, which we already showed. So, this was the method table. Okay. So, we have the methods of the superclass. So, for example, if you take this, there are methods from superclass and then our own methods and things of that kind. Okay. Now, when a class redefines a method defined in one of its superclasses, it is very easy. Just the method pointer for that method implementation must be stored in the same offset as the previous implementation of the method. We just replace it, nothing more than that really happens. So, if you take this, right, so there is no problem. See, for example, if phi is here also, fum is here. So, phi is being redefined here. So, I would possibly have a new pointer here. So, whatever phi was pointing to here will not be pointed to by this, a new method pointer will be placed in the same location, but the order is important. Okay. So, that is a very important thing that we need to notice. Then, so now the question is, so now what happens is when we actually call methods, when we call, for example, with when we have a method which belongs to the giant class, all these classes would have been compiled together. So, there is absolutely no problem if we pass this pointer, all the data members would be accessed appropriately. And when the method of the class MC is called, we still pass the same pointer. So, since the data area is ordered with the first superclass, second superclass, third superclass, etc., in that order, the methods can actually access these data members appropriately. There is absolutely no problem as far as accessing it. Every time we pass this particular pointer to this object, and since the data layout is the same everywhere, the methods can access the variables and execute appropriately. This is not the same in the case of multiple inheritance. So, let us see what happens in multiple inheritance. So, here is the picture. Here is class C, it inherits from both class A and class B. Okay. So, there are two classes from which it inherits. So, it has a method phi which is from class A, which has a method fo which is from class B, and it has a method fum which is again from class B, and there is a method phi which is its own. So, these are the method tables of the new class C. So, assume that C inherits from classes A and B, but that A and B are unrelated. So, we saw this already, these two are not related. Assume that class C implements phi, inherits phi from A and inherits fo and fum from B. This is something I explained. Now, look at the object layouts for that of class A. So, here is class A. Okay. It is not inheriting from any other class. Class B is also not inheriting from any other class, only class C inherits both from A and from B. So, for class A objects, we have a class pointer and then the data members of A, no problem. For class B, which is independent and unrelated to class A, there is a class pointer and then the data members of B. The trouble starts with class C. So, class C inherits both from A and B. So, should we place A's data members first or B's data members first? C's data members will always come after the members of A and B. So, that is not an issue. Should A come first or B come first? The trouble will be, if we have a method of class C which is inherited from A and it is called, then this the pointer to this object is passed here, right. So, it will expect that the data members of A appear here, that is because it works with the layout of objects for class A, which the members are right here. So, it expects that the members of A are right here. But if we call a method from C which belongs to B, it expects similarly the B data members immediately after the class pointer, that is in this area, because that is the way it is used, it is happening in the objects of class B. So, but if we place B here, then the method call of A will be inappropriate, and if you place B here, then method calls of B will be inappropriate. C will always work properly because it is always after A and B. How to solve this problem? So, that is what is mentioned here. When C dot phi is inherited from A is invoked with an object layout as here, it finds all of A's instance variables at the correct offsets, no problem at all. Since phi was compiled with class A, it will not find and cannot access the other instance variables present in the object and hence works correctly. So, there is no problem, C dot phi will work well because all this was compiled together. Similarly, C dot phi also works correctly implemented in C, because this is we are assuming that A is first and then B. Okay. So, that is why this C dot phi works properly. So, C dot phi also works properly because everything was compiled together, A and B are placed and then C is placed. But C dot fo or C dot fum will not be proper. So, C dot fo or C dot fum are from class B. So, with this arrangement, as I mentioned, B is supposed to be expected here, but B is here, therefore, it will not work properly. Fo and fum are inherited from B, but invoked from an object of class C. Instance variables of class B are in the wrong place in this object record, sandwiched between the instance variables of classes A and C. In objects of class B, the instance variables are at the start of the object record, they should have been here. Hence, the offset to the instance variables of class B inside the object record of class C is unknown. So, this is a problem. Where is B? The solution to this problem is, to compensate this, for this the compiler must insert code to adjust the receiver pointer so that it points to the middle of the object record, that is to the beginning of the B's instance variables. So, what we are saying is, if we know that this is the beginning of B, which we will know, okay, if this is the layout, we know how many data members are here. So, we will know what is the offset, this offset plus this offset will be known to us. So, if we make sure that we point the object pointer to this particular point inside this record and then call the methods of class B, everything will work out very well. Okay. So, because the B's data members are expected to be in the beginning. So, if we point the pointer here, this will be the first set of data members and it will work correctly. How do we do this? One is called the fixed offset method. Record the constant offset in the method table along with the methods. So, for example, for C, the offset of phi is 0 because C was compiled along with A and B. So, there is no, we can pass this pointer itself and everything will work properly. This is the extra offset. For phi, which is A's method, again the offset is 0 because A's data members are always here and A expects that they are in this place. So, nothing wrong, only B creates a problem. For B, the offset is 8 both for fo and for fum. So, the generated code actually, so assuming that the variables of class A take 8 bytes. So, that is this portion requires 8 bytes, that is the assumption. So, the generated code adds this offset to the receiver's pointer address before invoking the method. So, if we were pointing here, we add this and then it will point here. Okay. So, now everything works well. So, that is data pointer for C dot fo is pointing to this point, otherwise it would have pointed to this and then we had a problem. The second is, so this was actually adding this offset. Okay. So, whatever offset I showed here, this 8 was added, an instruction was generated to add this offset to the receiver's pointer address and then call the method. The other is what is known as a trampoline function. So, we create a trampoline function for each method of class B. So, for example, a function that increments this pointer, that is the pointer to the receiver, by the required offset and then invokes the actual method from B. So, we were doing it by an explicit instruction. Now, we have a special function that increments the pointer by the required amount and then invokes the actual method from B. So, this is just using an extra function. On return, it decrements the receiver pointer if it was passed by reference and then gets back. So, now you may wonder whether this is efficient at all. Trampolines seem to appear to be more expensive than the fixed offset method. Is that so? But not really so. For example, they are used only for calls to method inherited from B, whereas the other method, fixed offset method, the offset possibly 0 was added for all calls, whether it was from A or from C, the offset was added, you added a 0 and then that instruction was anyway executed, whereas here we do it only for the methods of B. And method inlining will make it better than option 1 since the offset is a constant. So, we do not have to take it out from any table like in the previous case, this is actually a constant. So, inlining will make sure that you use a constant addressing mode which you can utilize a constant operand. So, and since it is used only for the methods of B, this may be quite efficient. And a duplicate class pointer pointing to class C may need to be inserted just before the instance variables of B. So, let me show why. So, for example, if we had been pointing to this place for the when we had calls to the methods of A or C, what we really need to do is when we call the methods of B, we insert this class pointer here. Okay. We insert this here and then point it to the beginning of this class pointer and call it. So, that it looks exactly like this. Okay. It is as if we are calling something of class an object of class B is being passed on. So, this is more for convenience, not exactly essential for the operation. So, at this point we will close this lecture and in the next lecture we will look at some optimizations which can be performed on object oriented language programs. Thank you.